Okay, this is lecture 4. All right. Yeah. Okay, so we know a single alphabet with the index of coincidence is 0.0667, okay? Well, what if we have multiple alphabets? Because remember, the reason it was 0.0667 is because you have more E's and stuff like that. So that's what y'all remember how we just did a slide on that. Oh, okay on that, okay? Now, if we have 26 alphabets, in other words, the variance of the frequency of the letters would end up being, will be gone. So that's why we end up with infinity alphabets, we end up with 0.038. Okay. Let's look at this example here. So what if the letter T is encrypted with one alphabet, the letter H is encrypted with a different alphabet, the letter I is encrypted with a third alphabet? So say one is in English, one in Spanish, one in French or something, okay? But it's 3 different alphabets. So then S is with the first alphabet again, I was the second alphabet, S was the third alphabet, so on and so forth. Then it's 1, 2, 3, 1, 2, 3, 1, 2, 3. Everybody with me so far? Think of this as a different alphabet. So how could we choose this? Or how could we break this? Well, there's something called frequency distribution, which actually we're going to get to in a second, but when making this, you want it so that the frequencies end up being flat. So we don't have more E's than anything else. Okay? You know how we saw in English we have the most E's. NL, STR, and E are the most common 5 letters. So choose your alphabet so that the frequencies are flat. In other words, there's no one that's more than the other. So that's an easy way of making it tough, and we're going to see how to break that here in a minute. Okay, let's talk about a couple of different types. There's something called the Veneer Cipher, or as one of the teachers when I went to a boot camp called it the Veneer. It's actually the Veneer. It's based on the Veneer tableau, which is 26 possible alphabets. So here you can see the plain text, but soft. I forget what's that darn phrase?
Soft, what light through yonder window.
There you go, that's the one. But soft, what light through yonder. I can never remember the thing. But if we were to use that and encrypt it with a key, and the key happens to be the word Juliet, so the J is one alphabet, the U is one alphabet, the L is a different alphabet. So encrypting with a different alphabet, the keys vary. You can also remember the Caesar cipher, how they all shifted? What if each one shifted a different value? It would kind of be the same thing. Okay. Now, here's what the Veneer cipher looks like. So you see there's different alphabets. So if we took the B is the plain text, and the J. So if we took the B right here, and the J, we end up with the K. You see that? The B and the J gave us this K right here. Oops. See how they got the K? So if we did the U and the U, so over here we take this U, cruise all the way over to this U here. Is that U? That's V. Okay, and we get O. Y'all see that? I keep going the wrong way. So that's how they got the O. So you see how this is working? A little bit better than the Caesar cipher. So the key is a word that comes from the top of this chart. Really doesn't matter if it's the top of the side, as long as you don't mix them up. Right. Everybody okay with that so far? All right. How can we break this? This cipher was considered unbreakable for 300 years. It says in 1893, a Prussian major, Koziski, proposed a method for breaking this cipher. Okay. It says consisted of finding the length of the keyword and then dividing the message into that many simple substitution ciphers. So then we could do frequency analysis on them. So, what frequency analysis is, say I took some text, and if I looked at this text and found out that E was the most common letter, obviously it was probably English then. So you could very easily check out the frequency of a letter. So if I took a large amount of text, and if it was in English, and whichever, say it was encrypted with something, but whichever letter came up most, I would just replace that with an E, because that's the most common letter in the English alphabet. Whatever the second most popular letter, replace it with whatever the second most popular letter is in the English alphabet, which I think is the E. No, N. N. E's first, N second. So, okay? Kind of understand what I'm saying? Okay. It's nothing special there. So how does this work? Here's how the Kaczynski method works. You will have to do this. I will show you an example. Find repeating patterns of 3 or more. The longer the pattern, the better. I think the one you're working with is 15. For each pattern, write down the starting position of it. Okay. Then compute the difference between the starting positions, which I'm going to show you an example. Then factor these out, and then the key length will be one of the factors. Okay. So here's an example. So for this picture, just look at the C. Don't worry about the rest of it. Okay? Just look at the third line down of each. So you'll notice we have VLZIUD. Everybody see that? We have the same here, VLZIUD here. We have the same VLZIUD here. So we have a repeating pattern. Okay? You find it where the starting position is. Now, ciphertext is normally broken into groups of 5. The reason for that is just makes it a little tougher. A little bit tougher to read, that's all. Okay? So, and if this is 1, this always starts at 1. Everybody get that? Starts at 1. So many people start at 0. Okay, this starts at 1. So if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Everybody see how that's 20? And keep going. This ends up being 83, and this one ends up being 104. Okay? Then we subtract the differences. What's the difference between 83 and 20? That'll be 63. So 83 minus 20 is 63. Then everybody know how to factor a number. The factors of 63 happen to be 3, 7, 9, 21, and 63. Okay? Then we find the difference between 104 and 83. That distance is 21. The factors of 21 are 3, 7, and 21. Don't include 1. 1 is the factor of every number. Okay? Don't include 1. Do not submit 1 as your answer. 1 is the factor of every number, so don't include that one. Okay? So, if our factors are 3, 7, 9, 21, and 63, and 3, 7, and 21, what are our common factors? 3, 7, and 21. So the probable key length is either 3, 7, or 21. Well, if we look at the key at the top, what is the length of our key? It's 7. It's Dickens, 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 Dickens. So the key length is 7. Does everybody see how that worked? Pretty darn simple. Okay? The only reason I gave you the plain text is you can just see where the ciphertext came from. Okay, but really to do this, you're looking at the ciphertext only. Find the repeating groups of letters. The longer the better usually. I think on yours you have to find 4 repeats of 15 each. I think I tell you that. Right? So far so good? Okay. So how can we make things that can't be broken? How about an infinite non-repeating sequence of alphabets? Okay. Obviously if there's no repeats, Kaczynski's method is not going to work. What if we had a one-time pad? Okay. Or a long string of random numbers, or a Vernon tape, which is paper tape, or a book cipher. There's a lot of... What if we had a key that basically started a specific page in the Bible and went from there on? That would be non-repeating. Okay? So a lot of different ways about that. Okay, so what if we had dual message entrapment? So the message is, this message is crucial, yet the key is disregard this message. So actually, which one's the right one? I think, okay, I have a picture of that in forensics when we get into steganography, where Francis Lord Bacon actually had it that, the message said one thing, but if you looked at the font of his message, certain letters were different, which basically says flee. So the message said, come until I get you, but actually if you looked at the letters that were written differently, it says flee. So same kind of thing here. Okay. We could also have transposition ciphers. So the message reads, is this message is to show how transposition ciphers work. And if we have a column of 10, basically every 10 you wrap it. Think of it like a typewriter. Every 10 you hit enter. So the ciphertext ends up being up and down. So what you need to know is the column length. So again, this is just many different ways to do it. So far, so good. Ever seen these? Okay. Or how can we break that? Look for repeating characters, ENs, REs, TH, so on and so forth, and keep going, basically increasing your width until you start getting letters that make sense. Okay. Easy enough there. Yeah, that's pretty much how you break it. There's just an example. You don't need to know how to break that, but that's just one way of doing it. What if we had dual columnar transposition? In other words, column of 10 and take that result, put it into a column of 15. So think of it, Caesar cipher, we encrypt it with 3, then we take that result and encrypt it with 5 or something. We're just mixing it up. So, okay, just different ways. How can we break that? There's a relationship between them. You don't need to worry about that. We're not going to go into that. But there is a mathematical relationship to it, and there it is. Okay? Which you're welcome to read over if you like. How about product ciphers? Combine 2 or more approaches. What if we take our plain text encrypted with a key, then take that that E1 encrypted with a different key? Okay? It's kind of like triple DES does, but they do it 3 ways. Encrypt, decrypt, and encrypt, which we'll learn about later. There's many different ways to make it so people can't read it. Claude Shannon actually wrote a really good book called Good Ciphers, Characteristics of Good Ciphers in 1949. It says the amount of secrecy needed should determine the amount of effort needed for encryption and decryption. So if I am encrypting my pizza delivery order, does it really need to be something that's going to take 1,000,000 years to break? No. So what if I tell you DES can be broken in 21 hours? So I got something that only has a value for 20 minutes. Is DES acceptable even though it's been broken? Yeah. So, it's kind of, how powerful machine do you need based on what you can be using it for. Okay. Okay, keys and encrypting algorithms should be free from complexity. That was the problem with DES. Once we get to it, you'll see it's very complex. But why? There's no reason for it. Okay. Implementation should be as simple as possible. If you make things difficult, what happens? People screw them up. Okay. Errors should not propagate in corrupt message. You would not like it. So basically, if we got this big old long message and there's an error in block 1, we would not want the error to propagate to block 2 and 3 and 4. Maybe keep the error in block 1. You ever watch like a Netflix video or a YouTube video and the video gets kind of screwed up at one point? It kind of corrects itself and you do get to see it. What if that correction propagated through the whole video? Then you wouldn't be able to watch it. That's what he's talking about there. And the last one, the ciphertext size should be less than or equal to the plain text size. In other words, if we have plain text that's 80 characters, the ciphertext should be 80 characters or less. You wouldn't want plain text of 80 characters turns into ciphertext that's 200 characters. Wouldn't want that. Okay? Trustworthy encryption systems that are based on sound math. People have looked at them and understood them. It says analyzed by competent experts who have found it to be secure. Stood the test of time. So, think about it, the Veneer Cipher lasted 300 years. That's longer than AES has lasted, because it hasn't been 300 years yet. But you think in 300 years AES will still be out there? DES didn't last that long. So, alright, some examples. DES 1977, it still lasted quite a while for what it did. RSA, which is still used today, and AES, which is still used today. Okay. Alright, now let's talk about confusion versus diffusion. You will have to know this as well. Interceptors should not be able to predict the effects on ciphertext by changing one character. So if I have my plain text, and if I change one character, I should not be able to determine what happens in my output of the ciphertext. That's confusion. Okay. If we can change one character, then that's not good. Okay. Should be a complex functional relationship between key pair and ciphertext. Also diffusion, if I change one character, it should affect the multiple parts of the ciphertext. You do not want it where if I take my plain text and change one character, it changes one character in the ciphertext, and it's always the same character. You don't want that. you want it, so if I change one, it changes multiple values in different values in the ciphertext. We'll see examples of that when we start doing AES and stuff like that. Okay. Stream versus block. Stream is we're encrypting things as we get them, maybe one at a time. Okay. It's a high speed of transformation. In other words, we're transforming it as we get them. Okay. Low error propagation. So if I'm typing and we're sending the letters across one at a time, if I miss one letter, obviously that one letter is going to cross incorrectly, but it's not going to affect the prior letter or the next letter because I'm doing one letter at a time. Low diffusion. Again, it doesn't mix my message up at all. And it's also susceptible to malicious insertions. Someone could get a hold of my stream and insert stuff into it. Block ciphers, which are much more popular, like the transposition cipher. There's low speed of transformation. We have to get the entire block before we send it. There is a high error propagation. If we screw up something inside that block, it's going to affect the whole block. Hopefully nothing beyond that, but it could. And there's also a high diffusion. We want to make it so our plain text, if we change one value, it's going to change the whole block. And it's also immune to malicious insertions because we have the block and we can tell if something's been inserted into that. Okay. You do need to know this right here though. Okay. Breaking them. Crypt Analysis. We have a ciphertext only attack. So we know what the ciphertext is. We're trying to figure out what the result is. Kind of like the Enigma machine, if you think about it. They had the ciphertext. They tried to figure out how that was done. What if we have the known plain text? So we know what the plain text is, we just don't know what the output is. Or probable plain text, we think we know what the plain text is, or chosen where we know the process. Or what if we know the algorithm and ciphertext? So, different ways of breaking encryption. That's the end of that one. See, that was a short one. That's lecture 4.